in this screencast, we will finish looking at some examples of theorems in hyperbolic geometry. This helps us understand, these three examples will help us understand the connection between distances and angle measures. So here's one. For every epsilon greater than 0, there exists an isosceles triangle ABC such that the angle sum is less than epsilon. Now think about that for a moment. In hyperbolic geometry, we can make a triangle whose angle measures are as small as we choose. Now that's wild. So, oh, I'm so sorry. We will suppose that epsilon is greater than 0. Here's what we're going to do. We're going to choose A to be large enough so that kappa of A is less than epsilon over 4. Should make epsilons the same. What? Epsilon's a teeny tiny positive number. Think about a teeny tiny positive number. Then divide that number by 4. That's what you want to be. So you want to find on the kappa function an A that's really, really big so that kappa of that A value is less than your number. Remember, the kappa function is a decreasing function. And so as it's decreasing, it eventually crosses this threshold. Where it crosses this threshold, that's A. So now we construct a right triangle PAB with PA equal to AB equal to little a. Here's an A, here's an A, right? Like, why did we bother with this piece? We bothered with this piece so we would know that these connected. So here's P, A, B. Well, then we just come through on the other side, right? And we find a point C on line AB with A between C and B and CA equal to AB equal to little a. Then triangle CPB is the desired triangle. It's isosceles, and every angle has to be, sum of the angles is less than epsilon, because this angle measure is less than epsilon over 4, and this angle measure is less than epsilon over 4, and this angle measure is less than epsilon over 4 plus epsilon over 4. And so we add them all together, and we get a sum that's less than epsilon. So what's the takeaway here? We can make triangles with angle sums as small as we want, but we have to make the sides really big. For every epsilon greater than 0, there is a right triangle whose angle sum is as close to 180 as we want. We can make triangles with defect as small as we want. And the way we do this, oh golly, I'm so sorry. We construct an angle with measure 90 minus epsilon. Just think about it. Epsilon's a teeny tiny positive number. So think about a teeny tiny positive number. And then subtract that number from 90. And then make an angle that has that measure. Okay, so this has measure 90 minus epsilon. Call the vertex P. choose B on one ray and drop a perpendicular to the other. You pick B, you drop the perpendicular, the foot is A. This triangle has an angle sum greater than 180 minus epsilon, because these two angles add up to 180 minus epsilon. So the third angle's got a positive angle measure, so the three angles together have to add up to more than 180 minus epsilon. Now, we can make triangles with angle measures as close to angle sums as close to 180 as we like. And then this is true too. This is just bizarre. For every epsilon, every positive number epsilon, there exists a positive number d, such that if there exists a triangle ABC and the length of every side is less than d, then the defect is less than epsilon. We can make angle sums as close to 180 as we like. For sake of space, I will not include this in our video, but this is something that can be proven. Okay. It can be proven. I'm not going to prove it here for the sake of time and space, but you can ask me about it if you like. I'd be glad to follow up, Math 335 students. Okay, 7 minutes. We're good.